We also said we would initiate financing arrangements, and we did retain chartered bank, as Jack mentioned earlier. Just to give you a quick overview of the project, we're located right here. This is the outline of Cameroon, the capital city of Yaoundé, and our project is here in this box, and that's what you're looking at in this area right here. Our reserves at Kamuna, and that Kamuna deposit is located right here in this little circle. The reserves are about 54 million tons of proven and probable ore reserves, and these meet all international standards as far as quality control and applying the standards that regulatory agents accept. We average about 0.25% cobalt, nearly 0.7 nickel, and a little over 1.3% nickel. We've increased the resources in addition to that, and those are somewhat lower grade, but as we drill those resources out, there will be higher grade areas that we will convert into additional proven and probable reserves in the Kamuna area. Now, one thing to remember is that the Kamuna area is only about 4% of the total mineralized area. Everything you see here in red is mineralized area. And that Kamuna deposit right here is 4% of that area. The Mata deposit, located immediately north here, has reserves that are being calculated, estimated as we speak, but we already have estimated resources of over 220 million tons. A year ago, we had 145 million tons of resources in the Mata area. And again, that Mata area only comprises about 18% of the total red area that you can see on that map. The balance of the 5 other deposits are nearly 80% of the mineralized area. So just based on that slide alone, you can visualize how long this project is going to be around and what huge resources and reserves that are available to this project. This is a picture of our actual mine plan in the Kamuna area. These colors here are the first 5 years. Here's where we're going to install the process plant, where we crush and concentrate the ore and then process it through a leach process to produce relatively high purity cobalt, nickel, and manganese products. You can see immediately north of the plant in blue is a tailings area that is a permanent storage for all of the tailings that come from the plant. Now, we have a blessing in disguise here. You can also see large red areas in that tailings area. We have ore in the tailings area. That is that all of the overburden, the waste that comes from mining that in the pre-production period will be used to build the tailings embankment. So, you know, as they say, if you're issued lemons, make lemonade. And that's what we've done on this project. Everything that we see that Mother Nature has made available to us, we've taken advantage, we've recognized what it was, we've tested it, and we've put it to good use to make this project virtually the best that it can be. Now, this is a cross-section through the mine area. You can see the mine itself is only about 16 meters deep, which is only about 60 feet. So this is a shallow mine. As I say, I've never mined a deposit this shallow in my life. I've never mined a deposit where the trees are taller than the mine is deep. But what we're going to wind up doing is taking the overburden, and we've got a method that Brian Briggs, who you met earlier, brought to us and said, look, instead of hauling this waste material out in the truck and then dumping it back in, is to go ahead and cast it right in the open hole so that we're backfilling as we proceed, the same way as many coal operations are mining. And this allows concurrent reclamation, and it reduces energy costs, diesel fuel, labor, tires, truck time, mechanical time, and so forth. And it really lends itself for this deposit. The topography and the basic outline, the formation of the way this deposit occurs allows such method. And this is another example where whatever Mother Nature provided to us, we recognize what it is and taken advantage and put it to good use. The ore is only about 6 meters thick, generally throughout the deposit, and a lot of that is all in one interval. So it does provide for low-cost mining, as well as I said, concurrent. The key processing attributes on this, we take the ore and we physically upgrade it, we concentrate it. We crush it, wash it in water, wash away the fine material, which is low-grade waste. We wind up with a concentrate of high value. And that concentrate is only 20% of the original ore weight, but it's 3 times the cobalt grade. And that is the driver to this project. If you were not able to concentrate this ore before you go into the expensive leaching process, you would not have a project. That's how important that physical upgrading is. And it's as simple as a sand and gravel operation, literally. So it's, but once you get into leaching, now you're starting to get into more sophisticated metallurgical processing. If you compare our project compared to a copper mine or a gold mine, processing on that, we're complex. If you compare our project to all these other nickel projects around the world, in Australia, the Philippines, and Madagascar, and so forth, we're simple. So we do have a lot of attributes, and we've recognized the unique mineralogy in this deposit and developed the concentration and leaching methods that best suit that mineralogy. This slide shows the metallurgical lab testing that's been done in Golden, Colorado by an outfit called Hazen Research. We've gone through leach and primary solution purification stages. That's what you're looking at here. We take the solutions and go through a secondary purification, because once we leach this and put the values in solution, then the more pure that solution is, when you precipitate cobalt, nickel, and manganese, you get higher purity products. And furthermore, what we're intending to do is take those purified leach solutions, and through a process called solvent extraction, you further concentrate and purify those solutions, where now you have very pure cobalt nickel solution, and by adding sodium carbonate to those acidic solutions, you then form a very high purity cobalt carbonate, which you can then oxidize to a cobalt oxide, and that can be sent to end users in the battery market business and so forth. Nickel, we will sell that as a nickel carbonate. Again, it's of high purity. And then the solutions that are barren or rejected from the solvent extraction, before that solvent extraction process, that's where all the manganese is contained. And we add a sodium carbonate to that, and we form a manganese carbonate, which also is used in the battery business, as well as many other applications throughout the globe. So we've gone through extensive testing to validate the process, determine what the risks are, assess those risks. That way we can engineer and design to overcome those issues that could crop up. Because we have spent extra time adding value to this project, but even more importantly, I think we've added, I don't know how much more added value we can do, but one thing we can do is reduce risk. And that's critical to us, because we need to get this project financed, and we also need to get it up and running where it'll produce a design capacity for, as far as I'm concerned, 100, who knows, this thing could go 200 years. These are pictures of a mixed cobalt nickel sulfide precipitate. We take that and re-leach it, and then that goes into the solvent extraction process, where we can separate the cobalt and nickel and make these high purity products. As I mentioned, we also, the solutions that are coming before the separation of cobalt and nickel, we add soda ash or sodium carbonate, we form a manganese carbonate product.